Now maybe you can intuitively understand what that means just from this few details alone. Personally, I had trouble with it. If you want to pursue it, fine. All right. Okay, so we can plug in these into the expansion formula, the weighted sum, in terms of these, and here's what you get. So this term here that I'm outlining here, they are your A and M's, okay? And this term, the whole thing, so that's your coefficient A and M. So the weighted sum of your eigenfunctions of 0th order, right? So this now is your corrected to first order eigenfunction, right? So, and the lambda here, we just make 1. Okay, so you've got something of this order, right? So this just comes from this. This was our basic assumption in perturbation theory, that you could expand it in terms of a power series in lambda. Okay, so this eigenfunction here, functions, because n of them, they are the eigenfunction solutions to the eigenequation with this Hamiltonian. So that your basic Hamiltonian plus your perturbing Hamiltonian H dashed. Right? Okay, and similar logic with the energy eigenvalues, eigenenergies, same thing. This is the corrected term for the energies. This is what the basic energy was. We calculated this. We haven't done this one yet. The second order term, E2, En2, but we can do that. So we can do that next, in fact. So again, I ask you to do it for homework. Not too difficult. A bit more complicated than the first power. So now we're finding the energy correction due to the perturbing Hamiltonian to second order, so E2. Okay, so go back 2 sessions ago. Plug in this for your En in the eigenequation. Plug in this for your eigenfunctions in the general eigenequation. You need a lambda here. Plug in this as the Hamiltonian in your general eigenequation. Put everything on the left-hand side, and therefore all the coefficients of the lambdas, the powers of lambda. So in this case, we're talking about the second power of lambda squared. So all the coefficients, the coefficient of lambda squared has to be 0. So do that, equate it to 0, and you'll get this expression. Okay. So this is your second order too. Second order correction to the eigenvalues of En2 here, and you'll get something like this, right? Now we gloss over this until the next session, and we start doing applications. And one of the questions, I think, was you're asked to find the energy shift, in other words the change in energies, the correction in the eigenenergies for second order. So you'll use this formula in the next session. Alright, now there's a problem. The problem, if you think about it, the problem involves this term. It involves this denominator. And you can probably guess where I'm going with this. What happens if this and this, these two energy values here are equal. And when would that happen? See, this is the eigenenergy, the eigenvalue, for the eigenfunction UN. And this is the eigenvalue, the eigenenergy, for the eigenfunction UM. Okay? And they assume to be different. We've been assuming in this theory that we've been deriving, we've been assuming implicitly that the eigenfunctions, the UN, are non-degenerate. Remember, we've done this several times, again, revision. What is degeneracy? Two eigenfunctions are degenerate if what? If they have the same eigenvalue. Okay? Two or more eigenfunctions are said to be, by definition, degenerate if they have the same eigenfunction. Well, if UN and UM have the same eigenvalue, same eigenenergy, E, well, then you've got a denominator here which becomes 0. So you're dividing by 0. That's a taboo in physics. You're not allowed. Physics hates infinities, as I keep saying. So you don't want that. So you've got a problem. What happens? What do you do? How do you do perturbation theory when you have degeneracy? You know, when some of your eigenfunctions are not unique. Sorry, let me put that another way. When your eigenfunctions are degenerate. So they're different in a sense, but they have the same eigenvalue. And hence these here could be the same value, and hence you're dividing by 0, and that creates a problem. So how to get around that problem? And well, it's the next session. But I'll say I did not fully follow the details from the text. I suspect pretty strongly that, again, this is one of his Davies' icebergs, where to understand it fully you need more theory at a higher level. Now maybe I'm just missing it. You know, maybe you're smarter than I am, and you'll say, oh yeah, I understand that. It's because blah blah blah. So well, yeah, hats off to you if so. But you know, it's an introductory text, so certain things I feel he just glosses over. So until next session.